Welcome to the Picarro Community Green Forum, an open space for thought leaders to discuss the ongoing challenges in gas, energy, and beyond. I'm Tracy Boyd, Marketing Director for Picarro, and the episode you're about to hear is part of our expert series covering methane data collection, leak detection, and emissions measurement. Our guests will share their perspectives on where the industry is and what is next, providing important insights into what is fast becoming a new language, the language of methane emission measurements, quantification, and abatement. Joining me today are Picarro's Francois Rongere, Senior Director, Solutions Architect, Climate and Safety, and Sean MacMullin, Senior Director, Software and Data Analytics. So at a high level, tell me about the different types of methane leak detection technologies available today. Sean, why don't we start with you?
Most methane detectors are based on one of two physical processes. The first being that certain wavelengths of light are absorbed differently by methane than they are by normal air. And the second being flame ionization. So this is based on the detection of ions that are formed as part of the combustion process. And so those types of detectors can be used for many different types of hydrocarbon measurements, but typically use methane as a standard reference. So from those two technological principles, there are two main approaches that are used for detecting methane plumes and doing quantification. So typically split into two categories called passive and active. So passive sensors are typically positioned at a distance which may be far away from the gas plume. And they measure the reflection or lack of reflection of the sunlight as it passes through the plume and gets reflected back to the source. And so typical implementations of these types of passive sensors are mounted to satellites. They could also be on aircrafts, helicopters, or even in ground-based sensors, such as optical gas imaging cameras. On the other hand, active sensors rely on some of these same principles of how methane absorbs the light, but here they require the instrument to shine a laser through a gas sample and then look and see what gets reflected back through the source. So in these implementations, the light source, the laser, and the detector might be fairly close to the gas plume, such as in a handheld system, or they might be at larger distance mounted to aircrafts or helicopters. And then some of these active sensors actually require the instrument to be directly within the gas plume to make a measurement, sometimes by pulling the gas into a chamber in which to analyze it. And so those types of sensors can be built to be very sensitive, measure very, very small concentrations of methane. And then for the gas leak detection applications, those types of sensors are typically mounted on drones or in vehicles or on handheld devices so that an in situ measurement of the gas plume can be made.
Okay, so a lot of options available out there. So help me understand, how do these technologies fit into the context of measuring methane emissions in a distribution network specifically, Francois?
Yes, thank you, Tracy. Yeah, and at first I would like to point out that detecting and measuring are two different things. So let's start with detection first. So as Sean has mentioned, you may take measurements from distance, and when it's for a satellite, for example, you may have challenges with visibility in terms of clouds, and that prevent the detection itself. So that's the first thing that you have to consider. Another issue is the resolution. For satellites also, you may have several meters to several kilometers of resolution. That can also prevent the detection of small leaks. And then the detection limit. For satellites and aircrafts, the detection limits is typically for a satellite about 100 to 150 kilogram per hour, which in terms of cubic foot per hour is about 5,000, which for distribution system may not be in the range of what is seen, because for distribution system, a very large leak is 10 cubic foot per hour. For aircraft, it's about 1 kilogram per hour, which is about 50 cubic feet per hour. There is a nice article from William Collins from Berkeley and a number of others that summarize this. It's been published in July, sorry. In July, and a good reference presenting these detection limits. Another important point is to consider is the fact that the detection limit itself which is helpful to qualify different detectors, is not a abrupt frontier. It's not, you don't see a leak and then for slightly larger, you will see it all the time. It's actually a gradient. Matt Johnson recently at CH4 Connections has made a very nice presentation about it, explaining how this gradient varies in function of the weather conditions. Also, the wind has an impact on the detection limit. So the detection limit, which is a convenient way to organize the different detectors, must be considered with cautious in order to take into account all the different factors that can impact it. On the other hand, you have also some issues with the SWAT. So the ability to cover a large enough territory or large enough part of the territory in order to detect the potential leaks in this area. For an aircraft, for example, this SWAT is very narrow. And a distribution system is not a linear asset. It's actually a sort of network. So with an aircraft, you cannot really cover with one flight a large part of the distribution system. So you need to do back and forth. And of course, in terms of effectiveness, you lose a lot of time from that. The same thing with actually the other side, the handheld device. The handheld device have a very small SWAT. It's actually, you have to be on the leak to detect it. So the challenge related here is to make sure that you cover everything. And that takes, of course, a lot of time by foot to cover every piece of asset very, very precisely to make sure that you are not missing a leak because you are a little bit away from it. So in that context, the vehicle-based systems are fairly natural for a distribution system. You have streets, the pipes are along the streets, the houses are, of course, along the street as well. So you cover easily the main and also the services because the SWAT is large enough when the wind is blowing the gas towards the car. And that way you can cover the system to be analyzed. Back to the problem of measuring compared to detection. What we said about detection is one thing, but detecting a leak is not enough to actually quantify it. More parameters need to be measured. And that's also required to be close to the leak and to detect or measure elements like the wind direction, the wind speed, the environmental conditions, and from there actually infer the flow rate of the leak.
Okay, so we've covered the different types of detection solutions, the pros and cons of each, really understanding how critical understanding detection limit is. Let's talk a little bit about how data needs to be collected and analyzed in order to measure the emissions of a distribution network. Sean, can you give us a little detail into that, please?
Sure. So I would consider this maybe in sort of three approaches in order to measure the distribution network. And so the first being what are called emission factors. These are engineering estimates, which are typically derived from spot measurements of leaks, most typically through these handheld measurements like Francois just mentioned. You have to be right on top of the leak, but you can then do a direct quantification of it. And so this is historically how emissions on distribution networks have been reported. And so while these devices are typically sensitive enough to be able to detect most of the leaks, the approach itself has a very large uncertainty because it's not practical to really do this at scale. So typically small sample sizes are used. They're not specific to any particular network, but more of an average representation. And even in some cases, very small, less than 10 spot measurements have been used to define the emissions over a full asset class on a particular network. So from there, we can extend that to a methodology where a direct quantification of part of the network is made, and then the result is extrapolated. So this is better than a static emission factor approach, but it's still challenging because of the very skewed leak size distribution. You need a large number of samples to really characterize and understand your network very well. And then it's also challenging to really represent the uncertainty involved in an extrapolation because you need to ensure that the part you've measured is statistically representative of the part you've not measured in terms of asset class, material types, pipe vintages, terrain, et cetera. So from there, really the gold standard approach would be a full measurement, a full direct measurement of the entire network. And so as Francois mentioned, vehicle-based is really a natural choice for a distribution network. The technology now enables this to scale in a way. It's quick, it's not invasive, and it provides broad coverage on the distribution assets. So here, the vehicle crosses the gas plume within a couple of seconds. It's able to then provide a direct measurement of the flow rate using the concentration and atmospheric conditions, such as the wind speed and wind direction. And really, most importantly to note in this full direct measurement approach is that it really gives you the opportunity then to not only report your emissions, but to reduce your emissions. And so prioritizing the largest leaks for repair is the most effective way to abate emissions. You really can't reduce effectively what you don't measure. So in terms a little bit more about the methodology then, so it turns out that there's, over the direct measurement, there's a bias which is introduced from this direct measurement of a very skewed distribution. It tends to give a measurement device a higher chance to overestimate the leak compared to underestimate it. And so we've developed a method which corrects for that bias in a statistical way. And then what you're left with is an uncertainty that's random in nature. And so that's really important because it means you don't need to be very accurate on the measurement of a single leak in the network in order to get a very small uncertainty on the total emissions. And so in controlled release testing for vehicle-based systems, they demonstrated typically about a 1 order of magnitude uncertainty, about a factor of 10 on the quantification of a single leak. And then once this bias is corrected, this uncertainty then reduces as more leaks are measured. So it can be the order of 10% or so uncertainty by the time a few thousand measurements are made, and even down to a few percent if order of 10,000 leaks are measured. And so then the result here is that you have, for each measurement made by the vehicle, you can assign that a certain leak size that will provide a fair estimate of the total emissions when it's summed over the entire network. And most importantly, again, this also really then enables the framework for quantifying directly the abatement efforts in programs where all the leaks are measured, but only the largest emitters are prioritized for repair.
Okay, interesting. So you are able to kind of adjust for that uncertainty, or at least understand it and make sense of it in the numbers. Francois, can you describe for me why a measurement-based inventory is so critical? Why is it so important today?
Yeah, and as Sean mentioned, I think measurement is critical because of the importance of methane emission in global warming. Most of stakeholders really want to have a qualification of the emissions very specific to a system or an area. In addition to that, as Sean has mentioned, is a way also to drive abatement in order to know precisely where to look at in order and to act in order to reduce emissions. There are emerging efforts in terms of standardization and methodology that is underway. GTI has launched a new activity around Veritas that aim to develop protocols that can be shared by the different stakeholders to characterize emissions based on measurements. Also, OGMP 2.0 include measurements in this higher level of characterization of the emissions in order to be more specific and better represent the different assets and network. And again, what is important in emission measurements is the ability to abate the emissions. And by doing these measurements, we have an opportunity to prioritize the larger emitters in order to treat them in first and get, by that way, the best abatement rapidly. And to continue to maintain the different assets in order to minimize the emissions by addressing the larger emitter first.
So I think that's a good place to end. I want to thank everyone for their time today. Some very interesting thoughts on methane leak detection technology, really discussing the art and science behind how these technologies can work for distribution networks and helping us understand why measuring methane emissions directly is so important. If you would like to learn more on this topic and to become a linguistics expert in methane measurement, as Francois mentioned, you can look up Veritas, a GTI Energy Differentiated Gas Measurement and Verification Initiative, the OGMP 2.0 reporting framework, and of course our own website, gas.picarro.com, for further information and further reading. Up next, we will continue this language lesson by discussing various abatement methodologies available to you and hear from more experts. Thank you for your time today.